So we have class today, which I'm going to go over 5D. And then tomorrow, during our tutoring session, I'm going to go over the buying versus renting project. So I do encourage you to look over that project before class tomorrow, and maybe take some time to watch the instructional videos so that if you have any questions, you have a chance to ask them then. Obviously, I'm going to go through the project, but it's always good to have an idea of what I'm talking about before I get going. So any questions for me before I launch into 5D?
I just have one quick question, Erin.
Yes.
Are you going to be recording tomorrow?
Yes, I will.
Okay. Well, my father just passed away. I don't know if I'm going to have be able to come to class tomorrow or not. So that's why.
Oh, I'm sorry, Dawn. Yes, it's obviously it's recorded. There's also a full explanation video in Online too. Okay.
Okay. Thank you. I just want to make sure I don't miss anything.
Nope, you're good. All right, I am going to get going. So we are in 5D, we are making the switch from talking about exponential equations to what we call logarithmic equations. And the reason we talk about logarithmic equations is because we need to be able to undo exponential equations. So here's what I'm talking about. It says recently a pond was treated for bacterial contamination. After being treated, the total amount of bacteria in the pond decreased by 25% each day. So the work that this first part here goes back to 5A. So if we look back at 5A, I'm going to go way far back. Bear with me while I flip through. We are talking about exponential growth and decay. Remember these formulas? Where if we have exponential growth, it's Q equals Q sub 0 times 1 plus R to the T. Or if we have exponential decay, it's Q equals Q sub 0 times 1 minus R to the T. So remember, Q sub 0 is the initial amount, T is your time, and R is your rate is your percentage as a decimal. So if we flip back to 5D, and we bring that formula with us, we know that if we're talking about it's got it's decreasing by 25% each day. Remember, the fact that it's giving us a percentage value tells us that we're dealing with exponential here. So we're going to have our exponential decay formula. And that is Q equals Q sub 0 times 1 minus R to the T. So if we plug in what we know, it says assuming the pond started with 100 parts per meter, I believe is what the ppm means. Parts per, I believe that's what ppm means. Parts per million, excuse me, not parts per meter. What am I talking about? Parts per million. So if we plug that in, we're going to have the quantity equals 100 times 1 minus, and it's going down by 25% each day. So we're going to do 0.25 and to the T. And we're going to remind ourselves that T is equal to days here, not years, because we're measuring this growth in days. So if I simplify, I'm going to have Q equals 100 times 0.75 to the T. So this is our general model for how we would model this, how much bacteria is in this pond at any given time, okay? So number 2 says we want to look at how much we have at each of these days. So I want you to take this formula here, and I want you to plug 0, 1, 2, and 3 in for T and tell me what you get. You can just send me in a direct message. So remember what you're doing is you're plugging these values in for t. So for the first one, I would do 100 times 75 to the, or 0.75, excuse me, to the 0 power. Remember, anything to the 0 power is 1. So 100 times 0.75 to the 0 is just going to equal 100. So then for the next one, we would do 100 times 0.75 to the first.
Aaron, do we round to the nearest whole number since it's bacteria?
No. We're gonna do with 2 decimal places.
Aaron, do we take the 0.75 and put that to the exponent first and then multiply it to the 100?
Yes.
Okay.
All right. Sorry, my iPad stopped mirroring to my laptop. Okay, so when we plug 1 in, we're gonna have 100 times 0.75 to the first, which is 75. And then we're gonna do 100 times 0.75 to the second, which is 0.5, oops, not point, excuse me, 56.25. And then on day 3, we're gonna have 100 times 0.75 to the third, which is 42.19. And what is happening here is every time we're taking 25% off, but we're taking 25% off of the new value. And so this is exponential decay. And so if we look at an exponential formula, or what the graph of this would be, let me pull up Desmos so you can see what I'm talking about.
Is this what what we were doing with the spreadsheet last week? Almost, where it's decaying by 1%.
Yes. So here, let me show you what the graph looks like. So what we can see here, this is really zoomed out, but if we zoom in, we can see that these are down on day, like day 1, 2, 3, 4, and 5. So if we scroll up again on day 0, there's the 100, right? It's right here on the y-axis. But right here we can see on day 1 where it's 75. If we go to day 2, we can see that it's really close. Let's see if we can, oh, I almost had it. 56.25, right there on day 2, right? Day 3. Come on. I don't know if I'm gonna get it exact because again, this is approximating for us. But we can see that it's right there around that 4219 amount, right? Day 3 for 42.188. So again, it's going to keep decreasing because we're taking 25% off the new reduced amount each time. And eventually it looks like it gets to 0. But if you run your cursor along here, you're going to notice that even as you go out each day, you're still going to get values there. We will never actually hit 0. It just becomes really close to 0. And so I know on the graph it shows that it's 0, but again, that's because it's doing its best to approximate. It's not going to cross this line. It's not going to go into a negative amount. And so it's going down and approaching 0 would be considered its limit. Oh man, we're gonna have a fun technology day today. So if we look at the T part, I know you can't see my my table right now, but under the T box, you would just want to write 100 times 0.75 to the T, because all that's doing is just saying, again, what would we use for the generic formula there? So bear with me, I have to restart my iPad again. I don't know what's going on with the technology today. So number 3. Number 3 says, using our equation for number 1, how can we solve for them for when the amount will be 50 exactly, or exactly 1/2 the original amount? So remember, our formula is Q equals 100 times 0.75 to the T. So remember, Q is our value at any given time, right? So if we want to solve for Q with 50, we're going to plug 50 in for Q. So if we think about our steps, order of operations, we would divide both sides by 100 because we're trying to isolate T. And dividing by 100 would give us 0.5 equals 0.75 to the T. Now, T is in the exponent, okay? So we can't divide off 0.75. That's what a lot of students try to do, because again, it's the exponent part. It's not 0.75 times T. And so with what we know so far, we can't solve this.
Maybe this is a stupid question, but why can't we You know, not square root, but
So if it was like t squared, we could undo the square root because square rooting is the inverse of the exponent 2. But we don't know what the exponent is, right? That's where our variable is. So we don't have a root number that we can take of that in order to simplify it. Because we don't know that root, and since we need to solve for that root, that's where logarithms come in, because they are the inverse of exponential equations. So again, in order to solve some exponential equations, we need to use logarithms. Logarithmic functions are the inverses. And so we've got a whole bunch of definitions. I'm only going to go through some of these because I don't want to get too deep into it, and I'll come back. But the basic idea is that if I have a to the m equals x, and I want to solve for, say, m, which is kind of the situation that we're dealing with. In order to solve for that, I'm going to say log base a of x equals m. So we're going from the base to the value it equals, then to the exponent. So log base a of x equals m. In the equation log base a of x equals m, a is the base. However, if a logarithm is just written as log 5, then the assumed base is 10. We also have this idea of natural logarithms, and I'll come back to those, because again, I don't want to get too deep into all the explanations without having an opportunity to practice them. So the first thing we're going to do is we're going to talk about how to evaluate these logarithms. So if we go to the next page, we have a change of base formula, because your calculator is going to assume it's base 10 for the most part. There's some new calculators that you press the log button and it'll ask you for what the base is and what the exponent is. But overall, your calculator is going to assume log base 10. And the reason for that, and how you know that that's true, is if you look at, say, this graphing calculator here. Let me show you. You can see here the word log, L-O-G, and then in yellow writing is 10 to the x. So again, this calculator is assuming that when we press the log sign, the log key, we are dealing with 10 to the x, or 10 base 10. And again, so these are inverse operations that we're using the second key in order to get to them. So in order to be able to plug this into our calculator, we need to use something called the change of base formula so that we have the same base. So in our calculator, they're going to assume that these two bases are base 10. So I want to evaluate log 4 of 16, or log base 4 of 16. So first of all, this question here is saying 4 to what power equals 16? Well, we know that 4 squared equals 16. Therefore, we would expect, if we were plugging this into our calculator, to do log base 4 of 16 would equal 2. But again, we need to know, how do we plug that in? So we have log base 4 of 16. We're going to do log of 16. So I want you to think the numerator part is always the log of the larger number over the log of the base. So you'll see that I did log of 16 over log of 4.
where
So on
did
my
you
calculator, let's clear out this stuff. I'm going to do log, and I'll do 16, close our parenthesis, do the division sign, and then do log of 4. Again, close the parenthesis, press enter, and it does in fact give us 2.
Where did you get the 2 from originally?
Because so again, when we're doing, the whole idea of logs is that they're undoing exponential equations. So when it says log base 4 of 16, the question we want to ask ourselves is 4 to what power equals 16? Well, we know that 4 squared equals 16, right? So 4 to the second power equals 16. And therefore, I know, based upon this fact, that when I do log base 4 of 16, it's going to equal 2. Because we're saying 4 to what power equals 16. So if I were to rewrite this, right, let's say I had log base 4 of 16 equals x. Well, 4 to what power equals 16? Well, 4 to the second equals 16. So it's going to equal 2 when we plug it in. Now that's getting ahead of ourselves. Right now, we're just practicing putting these into our calculator so that we can evaluate them. But it is helpful to try to monitor what the answer is going to be. In number 2, I've got log base 4 of 1/16. So if I'm going to plug this into my calculator, I'm going to do log of 1 divided by 16 in the numerator, divided by log of 4 in the denominator. Again, this is just allowing us to evaluate these logs so that we can come up with an answer. So I want you to try plugging this in and tell me what you get.
I'm trying to find my division on my cap. Never mind. I got it. Never mind.
Okay. So when I plug this in, I get -2. But why would we get -2? Well, thinking about negative number 1, 4 squared equals 16. And if I do 4 to the -2nd, remember negative exponents turn our values into fractions. So that's going to make it 1/4 squared, which if I simplify is 1/16, which is why when I take log of 1/16 divided by log of 4, I get -2. So I want you to go ahead and do 1, 2, and 3, and then we'll talk about 4, 5, and 6.
Sorry, Aaron, could you repeat? Is it 1, 2, and 3?
Yes, just the ones that I'm showing you. Okay, so if we look at number 1, we want to put this into our calculator. We're going to do log of 64 divided by log of 8. And we're going to get 2. And again, the reason why is that 8 squared equals 64. I don't know why I just wrote 62 there. Equals 64, because again, doing log base 8 of 64 is saying 8 to what power? is 64. And number 2, we're gonna do log of 1/256 divided by log of 4. We will end up with -4. And again, why is that? That's because 4 to the -4 equals 1/256. And finally, number 3, log base 2 of 8. We're going to enter log of 8 over log of 2. I don't know what I just wrote there. There we go, log. And log of 8 divided by log of 2 is 3. Now, be very careful because, so again, we're putting these into our calculator, right? And so we need to make sure that we are ending the parenthesis before we put the next one in. So if I plug in, say this last one, I'm going to do log of 8. I have to end the parenthesis before I do division of log of 2. Because if I don't, I'm going to get a weird answer. So if I just did log of 8 divided by log of 2, it's going to give me some crazy fraction here, right? Or crazy decimal number. So you've got to make sure that you end that parenthesis before you put the thing in. Also, you want to make sure that when you're plugging this in, you're doing the large number, the of number first, and then the sub number or the base number second. So again, you don't want to do log of 2 divided by log of 8 because we're going to get a completely different answer. Okay, so you just want to be aware of how you're putting this in based upon how you're going to orient them. Number 4, 5, and 6 are dealing with some different situations. So number 4 says log base A of A. So log base A of A, if I were to plug this into my calculator, and yes, I know I cannot plug in the variables into my calculator, right? Or I can't solve this, but I have log base A of A, which is going to be log of A divided by log of A, which is the same thing. This is going to equal 1. Now it's not because I took the logs and I canceled them. I took the A and I canceled it, but because this whole thing is the same as this whole thing, then it's going to cancel out. And the reason for this is an identity, and it says log base A of A is equal to 1 because A to the first power equals A. So if I had, instead of log base A of A here, let's say I had, my room, let's say I had log base 9 of 9. Well, those are actual numbers. We're still going to get the same answer of 1 here because 9 to the first power equals 9. The second one, 15 to the log base 15 of 9. When you're taking this and raising it to an exponent that has the same base, see how we've got this 15 equals log base 15, or not equals, excuse me, log to the log base 15. Those are going to cancel each other out, and our answer is just going to be 9. So 15 to the log base 15 of 9. Again, these cancel each other, and this is just equal to 9. And I didn't get into this yet, but we talked about E. E is the natural logarithm. E is the base of natural logarithms. So, well, 15 and log base 15 cancel. Ln, the assumed base here is E because 10 and log go together, and E and Ln go together. Yes, Kaylee.
So is 15 and number 5, is that just multiplying?
No, it's the exponent. So we're taking
What's the first 15 then?
Yeah, it's not multiplying, it's saying 15. And then if we were raising it to the exponent, right?
Okay, so the log 15/9 is the exponent.
Yes, exactly.
If
So
it was
when-
multiplying, would the L and the 5 be even? Like, do you see what I'm saying? Like, would they be on the same? Would the log part be lower?
Oh, if I was multiplying them, then yes,
Yeah.
it would be written right next to it like that. If that
Okay,
if
I
this
just-
was multiplied together.
Okay.
Yeah. So because E and ln are inverses of each other, raising E to the ln will cancel that out and it'll just equal 6, much like the same way of 15 to the log base 15, those cancel each other by raising it to its inverse exponent. They cancel out and it just equals to the value. Kaylee, did you have another question?
Nope, sorry, I forgot to lower my hand.
Okay. So the next section is just, we're going to practice just switching between the two ways of writing them. We're not actually solving anything. We're going to get into solving equations in 5E and 5D. We're just working on moving these pieces around. So if you remember from the first page, if I have a to the m equals x, then if I want to switch from this, I would do log base a of x equals m. So it works in sort of this circular motion. So if I'm coming out of it being in logarithmic form, I'm going to do a to the m equals x. So if I apply this, what I have written here is log base 5 of 625 equals 4. This is a true statement. If I were to enter this into my calculator, log of 625 divided by log of 5, I would get 4. I'm not questioning whether it's true. I'm just practicing writing this logarithmic equation as an exponential equation. And in order to do that, I'm going to do 5 to the 4th equals, and the equals comes because I'm coming back across the equal sign, equals 625. That's all we're doing, is we're just practicing here, writing these in different formats. Okay, so if I go to the next page, again, we're just practicing these formats. Let me pull these notes with us because we're going to want this. Actually, hold on, we just want this. So in number 1, I have log base 4 of 5 equals r. Again, we're just writing it, we're converting it from a logarithmic to an exponential. So I'm going to say 4 to the r equals 5. So I want you to try number 2. Again, when you're sending me your answer, you're going to do your base, then you'll do your caret key to tell me the exponent. We'll do the next number. Then you'll press equal and the last number. So we're going to do 3 to the 1st equals 3. So looking at number 2, the log is on the left-hand side, and now looking at number 3, the log is on the right-hand side. That's okay. You're still going to be moving in the direction that leads you towards the equal sign and then over the equal sign. So what I'm talking about is we're going to do w to the negative b equals k, right? So we're still going in that circular motion. Yes, I know for number 3, we went counterclockwise, but again, we're going so that we're circling around the equal sign. Numbers 4, 5, and 6 look a little weird because there's not a base number written there. But that's when we want to remember. Remember, ln has an assumed base e. So we've got ln base e of 6 equals z. And with this, we're just gonna go e to the z. And I know this seems like we're using a whole bunch of variables, but remember, e is not a variable, e is a number. So e to the z equals 6. For logs, if there's not a base written there, we assume the base is 10. So we would write a little 10 in here. So we have log base 10 of 100 equals 2. So I want you to go ahead and do 5 and 6 and send me your answers in direct message. Okay, so number 5 is going to be 10 to the second equals 100. And number 6, we don't have that base, but we're going to put it in because we're reminding ourselves if it's ln, it's base e, and it's going to e to the y equals x. So now that we've gone from logarithmic to exponential, we got to go the other way. And the reason we're doing this is because we're going to start solving equations in 5e, and so we need to be able to move between these two formats to be able to solve them. So remembering that if I have 10 to the third equals 1,000, great, we knew this, we know that this is a true statement, but in order to put this exponential equation in logarithmic form, we're going to say log base 10 of 1,000 equals 3. Now with the log, when the base is 10, it's not always necessary that we write the 10 part. We're practicing here to remind ourselves where the base part goes, but we could easily have just said log of 1,000 equals 3. But again, practicing where that base is going to go is really important. Now, it's really difficult to obviously send me these in a direct message. What I want you to do, if you were to send this to me, you're going to do log and then 10, another 1,000 and equals 3 is how you would send that to me, because I know what you're trying to say. These are not, again, I don't want you to think that this is actually, let me have you, I don't want us to confuse ourselves, because this is not multiplying these together. So we're going to do an underscore 1,000 equals 3. Because again, what we're doing is we're saying log base 10 of 1,000 equals 3. And I don't want us to think that we're really doing log of 10 times log of or log of 10 times 1,000. I don't want you to confuse your notation. So if we were to do it in number one, we're gonna do log, and now the base is 5 of 1/125 equals -3. So I want you to try number two and send me your message, send me your answer in a direct message. Now, in your homework, when you're entering these, they're gonna have an actual, like, it's gonna say the word log, and they'll have like boxes of where you need to put the information. So you won't be having to worry about like formatting in terms of typing it in like you are to me right now. This is just so that we can practice sending each other information, right? So we would do log base P of V equals M. Now, like above, we have the values again swapped because we want to practice. What does it mean when we're doing this? So we're always moving away from the base. And so what I'm talking about is that we have 16 equals 4 squared. Completely true. So we're going to say log base 4. So we always start with the base of 16 equals 2. If this is uncomfortable for you, you could rewrite it first to 4 squared equals 16, right? Just swap the sides and then convert it into logarithmic format. It's just up to you on what you prefer, okay? So if we go to the next page, number 4, it says e to the z equals 3. So do I use log or what do I use with this?
ln.
Yeah. So I'm going to do e. So I'm going to do the natural log base e of 3 equals z.
What does the ln stand for again?
It's the, so there refers to Napier logarithms, I believe is what it's, yeah, so we've got it on the beginning. Hold on, here we go. Where is it? Oh, it's right down here. Okay, so natural logarithms, also called Naperian logarithms, are logarithms with the base of e and written as ln of x. The number e is an irrational number with a value of e approximately equal to 2.71828. And again, the same relationships hold true for natural logs that hold for actual logs, right? You'll notice here, I wanted to draw your attention, we can write log base e of x, and it's equal to ln of x, like the notation means the same as long as you're making sure that you're using the e for the base. If you were to put this into your calculator, you would do log of x divided by log of e. But I would encourage you to get comfortable with and familiar with using ln when you see e, just because they are inverses of each other and that's what we should be relating to each other. You can use log, but you'd have to specify that it's base e if you were putting that into your calculator. So I encourage you to be using the natural log, the ln, when you see e present. So if we go back to number 4, I have ln base e of 3 equals z. We could write ln of 3 equals z, or like I said, well, it's not my preferred, we could still say log base e of 3 equals z. So to do 5 and 6 and send me your answers. So again, it's in exponential form. We want to switch it to logarithmic form. So we're going to say log base x of 6 equals 3. So obviously the way you're sending me your information, make sure you're writing it down the same way that I'm writing it down, not using our shorthand that allows you to send me your answers, okay? And number 6, because we have base e, we're going to say ln of 1 equals 0. Or if you really want to make sure you have that base value in there, you can see ln of e or base e of 1 equals 0. But again, it's redundant to put the e as the base of the ln because we already know that it's there. So we have about 23 minutes left in class. So I want to actually get into 5e so that when we come back from Thanksgiving, we have as much time to go over 5f because it's really big. So I'm going to pull in 5e right now. We'll get into that. Okay, so we've got some identities. If we have log base a of 1 equals 0, why is that true? Again, this is true because a to the 0 power equals 1. That's why it's true. Much like log base a of a equals 1. Again, why? Because a to the first equals itself. Any identities that are true for logarithms are also true for natural logs. If we were to interpret ln of 1 equals 0, it's because e to the 0 power equals 1. And ln of e equals 1, again, is because e to the first equals e. We have some ideas of exponential logarithmic equality. If a to the x equals a to the y, that is true if and only if x equals y and our a value is not -1, 0, or 1. So how would this work? Well, if I had a to the x equals a to the second, we would say that x equals 2 there. That's how we would solve for that. Because again, the only way that that relationship is true is if the exponents are actually equal to each other. That same relationship is true for logarithms. Log base a of x is equal to log base a of y, if and only if x equals y and x and y are greater than 0. We can not take the log of a negative number. So I want you to remember that. It's not possible. So how do we use this? So if you think about our steps, if we have we have log base a, I'll make sure I'm using the same letters. I don't want to mess up our method. If I have log base a of x equals m, remember to switch this into exponential, I'm doing a to the m equals x. So if I apply this to our example, I have log base 3 of x equals -2. If I want to solve for x, I'm going to do 3 to the negative second equals x. So evaluating this, 3 to the negative second, remember negative exponents, they turn our values into fractions. So this is going to be 1 over 3 squared. And 1 over 3 squared is 1 over 9. Now, if you were to plug this into your calculator, you're going to get a weird value, right? If we did 3 to the negative second, it's going to give us a decimal number of 0.1 repeating, and 0.1 repeating is 1/9. On your graphing calculator, you can get it to convert your value to a fraction for you. If you press math, and you can see it says frac here. If you press enter and you press enter again, it's taking our answer, you can see, and converting it to a fraction. You'll see that it gives you 1/9. And so if you're doing this and you're like, wait a minute, I have to have my answer as a fraction and not as a decimal, that's how you can get the calculator to convert it for you if you're not doing your steps yourself. So I want you to think about what we did in the example, and I want you to try number 1 and send me your answer. So we're going to take 2 to the negative 5th equals x. Again, in order to solve this, we had to put it in exponential format to get that variable out of the logarithm. We can't enter that into our calculator. And so 2 to the negative 5th is 1 over 2 to the 5th. And 2 to the 5th is 32. So we get 1 over 32 equal to x. Now, number 2, there's 2 ways we can solve this. What is one way that we can solve it using some of the steps that we've already done? Have we done anything with these, just the left-hand side yet?
Sorry, Aaron, what did you just say?
I'm just saying, have we dealt with something like log base 3 of 81 before? Ignoring the equals x, have we done anything with that yet?
I thought we did a problem like this in the last lesson.
So what did we do at the very beginning of 5D, right? We were just plugging these into our calculator. And so all we actually have to do here is log of 81 divided by log of 3, right? This is already set up for us to just enter this straight into our calculator. Now, don't forget, this doesn't mean you're doing log over log. Oh, those cancel out. 81 divided by 3, 27. Great, that's our answer. No, remember, all of this together, this whole thing is one number, and this whole thing is another number as well. So you're taking a number, dividing it by a number. You can't like cancel those logs out and use some fancy math that way. So we're just going to do log of 81 divided by log of 3. Dividing this out, we get 4. Now that is way number 1 to solve, right? We can do it that way. Or if we think about these statements we have up here of exponential equality, we can think, well, okay, if we were to turn this into an exponential equation, we would have 3 to the x equals 81. Well, 81 we can represent as powers of 3. 3 to the 4th power equals 81. So if I replace 81 with 3 to the 4th, the only way that this relationship could be true is if x equals 4. So all I'm trying to show you is that, yes, we can just take this and plug it into our calculator, and I'm fine if you want to do that. But I'm also saying there's other ways that we can solve it using some of our relationships that we already know. Okay. So if we go to the next page, I've got log base 3 of x equals 2. I want you to try that one and send me an answer in a direct message. So if we go through our method of converting this into an exponential equation, we would say 3 to the 2nd equals x. And evaluating 3 to the 2nd, we get 9 equals x. And number 4, it has ln of x equals 2.2. We need to remind ourselves what the base value is here. We know that there is e there. So I want you to try putting that into your calculator. Send me an answer that's rounded to 3 decimal places, please. So our process here, we're gonna take our base E, raise it to the exponent of 2.2, and we're gonna equal X, right? Because when it's in exponential format, or excuse me, when it's in logarithmic format, we need to put it in exponential format in order to undo that. And again, the reason we know that we need to do that is because it's telling us to take the natural log of a variable, which we can't do. So in order to solve for that variable, we have to convert it to exponential form. When we do e to the 2.2, it's a big long number. We get approximately 9.025. So number 3, we have log base 3 of 1 equals y. Now remember, you can plug this into your calculator, right? We could do log of 1 divided by log of 3, and we would get 0. But why do we get 0? Well, remember, what this equation is saying is 3 to the y equals 1, right? Like it's 3 to the what power equals 1. Well, the only way that I can get 3 to turn into 1 is by raising it to the 0 power. And therefore, again, the only way this statement is true using equality is to say that y equals 0. So you can use your calculator to solve it like I did on the left-hand side, or we can use our reasoning of our facts with exponents in order to solve it like I did on the right-hand side. If we look at number 6, actually, let's not do number 6, let's do number 7 first, and then we'll go up to number 6. There's more steps here, right? I have 5 times the natural log of x equals -20. And we want to solve for x. So we're going to have to unpack this to get at where x is. So when we look at this, it's really like this. 5 times the natural log of x equals -20. So I'm going to divide both sides by 5. So doing that, I'm left with the natural log of x equals -4. Now, this is a completely valid statement. This is okay, because we're saying that there's this base e that we're going to raise to a negative exponent, which is allowed, and it's going to equal some value. Now, there are other times when negative numbers are not allowed, and I'll show you examples of when that happens. But in this situation, this is a valid operation. So if we do this, we're going to do e to the -4 equals x. So again, this is how we are getting at solving for that variable by converting it from a logarithmic equation to an exponential equation. If I raise e to the -4 power, I get I have to press the second key and then the ln to get the e to the x. We can see it right here in little yellow writing. I'm going to do -4. And I get 0.018315, blah, blah, blah. So we're going to just round this off. And again, your homework will tell you how many decimal places to round. I'm going to do 4 for right now, but it will let you know. Okay. So if we use those ideas, let's go up to number 6. Okay. Thinking about how we had to convert this from logarithmic to exponential. So number 6, I have ln of 5x equals 3. Well, how 6 and 7 are different is that in 6, the 5 is within the natural log, where in 7, the 5 is outside the natural log, which is why we divided it off. In 6, I can't just divide both sides by 5 because the 5 is in with what we're taking the natural log of. Okay, so the fact that that 5 is in those parentheses means we can't divide it off. And so we first have to convert this from logarithmic to exponential. So if I remind myself, there's a base e here, right? And when we don't see one, we know with ln, there's base e. So I'm going to do e to the 3rd equals 5x. So in order to solve for this, we're gonna wanna evaluate what e to the third is. So we bring our calculator up. I'm gonna do e to the third. So we'll do second ln to get that e up. We'll do 3 inside there. And again, I get a big long decimal number. So 20.08553692. And that equals 5x. Now, as I've told you many times, don't round until the end. So I'm writing all these decimal places down, but ultimately I'm going to store this value in my calculator to divide both sides by 5. So for me, I'm just going to press the division key. So that's taking my answer, and it's when I divide by 5, it'll just take all the decimal places I can't see here and divide them by 5. Which gives me 4.017 approximately. If you wanted to do this all at once, you could do in parentheses, second e to the third, n parenthesis, divided by 5. And so that's telling the calculator to do e to the third power, then divide it by 5. And that's still going to give us the same answer. All right, that's a good stopping point because all the problems after that have to do with going from exponential into logarithmic. So I don't want us to push too far ahead. So I will pick 5e up when we come back from Thanksgiving. But tomorrow I'm going to go over the buying versus renting project. Okay, so if you get a chance to review the project, the videos, the layout, just so if you come, you have questions. So that's what I'm going to do tomorrow. And then if it doesn't take the whole time, that's fine. So that's what we got going on. Any questions for me before I let you go?
Nope, thanks, Erin.
All right. Well, I hope everybody has a good day. If I don't see you tomorrow, have a very happy Thanksgiving, and I will see you next week.
Thanks, Erin.
Bye, everyone.